Okay, it's 9:01. We're going to go ahead and get started. Good morning. My name is Chris Modrich. I am the VP of Sales and the valve subject matter expert here at Lesman. I'd like to thank you all for taking time out of your busy schedule to join us this morning. Our presentation, which we're calling Pressure Regulators 201 Beyond the Basics, will do a quick review of regulator fundamentals. We'll talk about using pressure and back pressure regulators and control loops. We'll dig into regulator accuracy and the effects of droop and how to improve accuracy. Tim will provide some tips on proper regulator sizing, and at the end, assuming everybody has time and is interested, we'll have a Ask the Expert session to answer your questions. Our presenter this morning, Tim Gaynor, is our Regional Sales Manager for Richards Industrials. Richards manufactures under the brand names of Jordan, Steraflow, and Low Flow. And under each of those brands, there's a nice variety of pressure and back pressure regulators and temperature regulators. Tim's got 26 years of experience in the industry, 23 with Richards, and is responsible for training and supporting the sales channel. As we go along, if you have any questions, don't hesitate to use the little questions box, and I'll find spots to drop in the questions as it makes sense. And if not, we'll save them for the end, depending on how many they are and how complicated they are. So at this time, I'd like to welcome Tim, our featured speaker, and Tim, have at it.
All right, thanks, Chris. And yeah, the only thing I would add to the topic of the questions, send them in whenever you think of them. You don't necessarily have to wait until the end, because we'll be changing topics here or there, and Chris will do a good job of bringing them up or addressing them. And if we don't know the answer, we'll certainly find it and get back with you. He already did a great job going through the agenda, so I'm just going to jump in. We want to try to keep this brief. We know everybody's time is valuable, so we're going to just jump in right away. Just real quick basics: pressure regulator, self-operating device, so fully mechanical, which work directly off of the medium, whatever it is that they are actually controlling the pressure of. Pressure reducing valve, PRVs, lowers the inlet pressure to a desired set point or the outlet pressure of the valve. So we're controlling P2, we're controlling the downstream pressure. Back pressure regulators maintain the upstream pressure, a normally closed valve that opens once you hit your set point. So again, basics, I'm pretty sure everybody has some awareness of that. So one thing that we want to emphasize here, the idea of this program is to talk about maybe more challenging applications that regulators can handle. And so one concept that we want to talk about is the idea of a regulator as a control system. And so what I mean by that, if you looked at a control loop, you're going to have a sensor of some type, a transmitter, for example. Well, in this case, the sensor is the diaphragm. Okay, that's what actually allows this force balance mechanism to work. In a control loop, you need some type of controller, something that is actually telling a control valve what to do. Well, in this case, it's the spring. That establishes your set point. By compressing the spring, you're establishing your downstream set point in a regulator. And then lastly, you need some type of feedback mechanism, something that actually adjusts per the signal of the controller. And in this case, it's the valve plug. So even though it's fully mechanical, you can view a regulator or a back pressure regulator as a mini control loop. Typical regulator applications, you're looking up to 20, maybe 25% accuracy. You're going to have some offset, and we're going to talk about how to minimize that. And then a lot of set and forget, to be cliche, functions: steam heating, pressure control, chilled water, cooling water, pressure control, plant air supply, tank blanketing for nitrogen padding, that type of thing. And then of course, pump bypass loops to keep pumps from deadheading, loop pressure and relief functions, all real common applications. And some advantages: obviously it's a mechanical product, so no power is needed to position the valve. There's no 4 to 20 or anything like that involved. You don't have to have separate measuring elements for feedback. They sense internally or through a downstream tap, but it's all mechanical. Designs tend to be simple, low cost, and high reliability. Set and forget, as we said earlier. There's typically no stem packing involved with these, and packing can be a source of leakage, fugitive emissions, that type of thing. So that's eliminated in regulators and back pressure regulators. And again, they're force balanced, so whatever it is they're controlling, they are actually in contact with. Some limitations, because they don't do everything. The media should be relatively clean, free of solids, and fairly benign in terms of chemical interaction. Materials of construction are typically limited. Operating points aren't constant due to droop. In other words, there will be some offset because it's a mechanical product. And they typically can't accommodate noise reduction or cavitation control trims that you would see in a control valve. And then failure modes are fixed. In a control product, you can choose failure mode in most cases, whereas with a regulator, like a basic self-contained regulator, is going to fail open 99% of the time. So some challenges, and we're going to go through each one of these and how to address them. So there's accuracy, of course, the offset that you might see in a regulator, shutoff class in the considerations, metal seated regulators versus soft seated regulators, how to apply those, what the challenges are there. High rangeability applications, they're limited on flow ranges. What can you do to address that? Regulators in series, so high differential pressure applications that are normally outside of the capabilities of a regulator. What do you do to address that? And then in general, some sizing and selection requirements in order to ensure that when you do apply a regulator or a back pressure regulator, it actually works as prescribed. So we'll talk about the accuracy first, or droop is a common term for this, offset. So all this is, as the flow through the regulator increases, there is a subsequent drop off in pressure. In a back pressure regulator, it's known as build or gain. The opposite is true. As the flow through a back pressure regulator increases, the pressure on the inlet side increases. And that's an important point. We'll get back to that here in a few minutes. And then obviously the lower the droop or the lower the offset, the better the regulator, and the better it typically is for the application. And again, most manufacturers will specify something in the range of 10 to 30%. Here's a nice representative chart of what we're talking about. So let's say this is 50 PSI, excuse me. Regulator set there, but as the flow increases, you'll see a drop. And the analogy that I like to use for people, if you're taking a shower and someone turns on a dishwasher or flushes a toilet, the pressure out of the shower drops, and it's because you've got more flow going through your home regulator, and it has to open more to allow for that. When it opens more, it changes the spring compression, and all of this curve is a function of that. Even the lockup, as the flow decreases and you move toward closed, there's actually a little bit of an increase in pressure to fully close the regulator, and that area is called the lockup. So very common in mechanical devices. It's just it's pure physics, but there are ways to combat it. So if you look at some basic units, the one on the left is your typical self-contained mechanical regulator. These are great when you want speed of response, you want to keep the cost down, but they're going to have some droop, maybe depending on the application up to 20% offset, which may not be good. You know, if you're supplying steam to a number of cookers, retorts, heat exchangers, and there's a lot of demand at once, well, you don't want to have a corresponding pressure drop because the regulator can't keep up with the demand. So that's the real world comparison or analogy rather, excuse me, that, you know, it's important for your heating and make sure you're getting the transfer that you need in a steam application. So one way to combat that is to go to a piloted valve like we have on the right. So these are, they're going to be a little slower reacting because the pilot valve is telling the larger valve what to do, but they're usually higher capacity, and a piloted valve will also have, will be more accurate. So now maybe we're in the 5, possibly 10% droop category. So much more accurate across a broader range of flows. So that's 2 steps that you can take to improve on the overall accuracy. And here's a little hierarchy of that. So the first one, self-acting, which we talked about, 10 to 30% piloted. We talked about 5 to 10. But then there's also air-loaded. Again, is that spring in regulator compresses and decompresses because flows are changing and the seat position is changing. That's where a lot of that offset is generated. But you can actually do an air-loaded regulator, which eliminates the spring, and then has essentially 0 droop, because you're not changing that compression at all because it's actually not even there. So a valve such as this can be a good option. Now you do have to supply some type of air signal. So you can see the port on the top here. Hopefully everybody can see my cursor. So you have to put some type of air signal onto the top of the valve, and whatever you put onto the top of the valve becomes the set point of that particular regulator. So again, you're looking at applications where now you still are in a mechanical product, but you're looking at almost 0 offset. So control valve accuracy, but without nearly the cost to actually install these. So a couple of neat little variations that you can do. Again, there's no spring, so how do you establish that set point? And this slide shows 2 very, very common ways. Now these are sanitary valves, but the same can be said of the industrial valve on the previous page. So the 2 applications I'm going to talk about are applicable to either style. But the one on the left uses an air set regulator. It's literally a point of use regulator, and you can dial in whatever PSI you want to the top of the valve, and that becomes the set point. And these are great for a couple of reasons. One, if you have a regulator or back pressure regulator that's in a hard to reach area, maybe it's up toward the ceiling of a facility, or it's on a skid and it's behind a lot of equipment, you can remote mount the actual regulator. Oops, sorry. You can remote mount this regulator and run tubing to this valve. So if you need to make adjustments, maybe for one product you have a certain PSI that you need, a certain pressure, but then other times you need higher pressure or lower pressure, and you can do all that remotely. And then the other one that we have here, this incorporates an extended range I to P. And the beauty here is now the same principle is there, where you can remote mount this and still do multiple set points, change set points without actually having to touch an adjusting screw or an adjusting handle. But the beauty of this is you can now control with a 4 to 20. So you send a 4 to 20 to this, and it converts the air signal and then loads the dome, and now you've established your set point. And this is a really neat sort of intermediary between a purely mechanical valve and a control loop. It's still not as costly, and it's actually faster because the regulator will sense at the regulator itself. It's not relying on a pressure transmitter downstream to actually send any kind of feedback. So you still have that interactive control of a 4 to 20, the ability to change set points, but it's then actually a faster solution than a control valve loop at that point. So moving on to another topic, shutoff class is something else to consider when you're applying these. And the most prevalent 2 that you see out there are hard-seated or metal-seated valves, and those are ANSI class 4 shutoffs. So their allowable leakage is 0.01% of rated capacity. And that's not a lot, but depending on the applications, it can still be too much. Metal seats, very common, general utility applications, and by that I mean steam, chilled water, glycol, plant air, nitrogen, a lot of very common applications that you see out there. The other seat material or seat type and shutoff class is soft seat, where you've got it could be Teflon, it could be EPDM, Viton. There's a lot of different materials available, and those are ANSI class 6 shutoff, which is bubble tight. It's still not zero leakage. So the bubble tight thing, not necessarily a misnomer, because it does have allowable bubble leakage that's based on size and CV and a lot of other factors. But where we see the class 4 items specified more are on, I don't want to say dangerous, but tougher applications like hot oil. So you don't want to have hot oil leaking through. If you're heating something and you want that flow to stop and you're using a class 4 shutoff, you're going to get leakage, and maybe in that particular application you may be overheating a process. Or boiler feed water, for example. If you have a valve that has anti-class 4 shutoff and you shut the boiler down over a weekend, well, you're going to have water leaking by that valve and you could flood a boiler. So a couple of situations that obviously are not going to be good for ANSI class 4 shutoff. So that's one of the key things that as a valve manufacturer, we like to know going into an application. We don't want to hear, I need a 2-inch valve. We want to know what's going to go through it. And these are two of the reasons why, because it can be a safety or, in the case of boiler flooding, a huge problem that results by just not having good information about shutoff class. Now, all that said, pressure regulators, back pressure regulators, are not designed to function as isolation valves. A lot of people, in an effort to save money, try to use them as both, but they're not designed for that. And even a soft seated valve, over time, that seat's going to deform. You're going to get degradation, and over time it'll begin to leak more than what it's designed for. So can't emphasize enough that they're not designed to function as isolation valves. High rangeability applications. So what we're referring to here is the ratio of minimum flow to maximum flow. Again, it can be steam, water, oils, doesn't matter. When you have a mechanical valve, there's just limitations on that flow range. For example, if it's water and you're trying to go from 1 GPM to 200 GPM, you can't do that in a mechanical valve. It's just that range is too wide. It doesn't have enough resolution to actually handle those flow range and still provide accurate, reliable pressure reduction. It's just impossible in a mechanical valve. But there are some ways that you can approach that and minimize some of that offset or some of that droop, for example. But in this case, we actually use droop as a positive, and one possible application or one way to address this challenge is by putting regulators in parallel. So, the desire here obviously is to stick with something mechanical. And if you put them in parallel, then you can take that flow range and approach it with, okay, the smaller regulator is going to handle about 1/3 of that flow. And then the larger one is going to handle 2/3. And then you just slightly stagger their set points. So just an example here, we'll use water again, but let's say that you're trying to control at 50 PSI. Now the smaller one you can set at 52. And as the flow increases, as we talked about earlier, the flow water through that increases and the valve opens more. Eventually it's going to drop below 52. And when it hits 50, then you have the larger pressure reducing valve set for 50, and then that opens. And at this point, you've got flow through both valves. And so with that 1/3, 2/3 arrangement, you can cover a much broader range of flows. And the nice thing is, when the flow decreases, you don't want to have both valves open again. So obviously as the flow decreases, the pressure starts to rise again. And once it goes above 50, the larger valve closes back off. And in a lot of cases, we see applications where there's high demand for startup. If it's steam, you're trying to heat up equipment, or if it's cooling water, you're trying to cool things down rapidly. And once you get things to their desired temperature, the actual required flow is pretty low. So this 1/3, 2/3 works great. If you are using this water for cooling, you get temperature where it needs to be, the flow rate drops dramatically, that larger valve now will close off when it gets to 50, and that smaller valve can handle maintaining the temperature. And you'll just be at 52 or 51 psi, and it's just doing its job because that's all that's required of the system at that point. Hopefully that makes sense to everybody. Again, mechanical approach to higher rangeability. And then regulators in series. And the challenge here is you have a high pressure application and you want to reduce that to a much lower value. Again, it could be anything, water, steam. Water brings its own challenges because of cavitation. So that's always something to consider. But here, just pick random numbers. If you're ultimately trying to go from 900 PSI to 125 PSI, most regulators cannot do that in one step. The delta P is too high, and you've got to remember that the downstream pressure is all you have to actually modulate that regulator. And if the DP is too high, the trim's not going to move and position itself the way it needs to. So the idea here is to two-stage it. Find products that can handle, in this particular example, a 400 PSI drop, and then something that can handle 375. Could be the same valve, just a little bit different size, and you still want to incorporate, flow rates and all that, and we'll talk about sizing in a few minutes. But in general, this is a good way to do it. The one caveat that you always want to make sure of is that the second regulator in series has a max rating above the inlet pressure of the first valve. So in this situation, you want to make sure the second PRV is rated to 900 PSI in the event the first regulator fails. They typically fail open. So now all of a sudden that second regulator could see 900 PSI. So having done this for many years, that's the biggest error that I see out there. The actual application's not that hard. It doesn't involve a ton of math. It's just, looking at allowable pressure drops and things like that. But people forget that that second valve needs to have a body rating equal to the inlet on that whole system, just in case there's an issue. Hope that makes sense. So valve sizing, we referred to this a couple of times. And the sort of joke that I used earlier is, I need a 2-inch regulator. And we get those phone calls a lot, but that leaves a lot to the imagination and doesn't give us much to work with. And if you look at the range of CVs that are available in a given line size, for example, the idea is to dial it in as closely as possible. So line size, obviously at a minimum, although normally the regulators are not going to be line size, and that's important. People always ask about costs, and if you size a regulator right, usually it's a line size reduction, and that helps save money. So we want to know the inlet pressure, obviously. We want to know the outlet pressure, P2. At least maximum flow. It's nice to know minimum and max, so that again we can see, can one regulator do this? Does it need to be 2? Is it beyond that that capability? But at least maximum flow, so that we know we're not going to starve the system. Again, using steam as an application, if we don't have enough capacity or CV in a regulator, all of a sudden your heat exchangers are looking for more heat, more steam, and we don't have the capacity, you're going to starve your system. And then what's going through it? The normal things, steam, air, water, those are pretty straightforward. But if you had something, like an oil or something viscous, we want to know the viscosity, the specific gravity, again, so that we can compensate for all those things. But by using all these, it allows us to actually pick the right CV for a given size. So if the inlet pressure varies, we normally would use the lowest of the inlet pressure. And if the outlet pressure varies, we usually use the highest. And the reason for this is, we want to have the smallest differential that the valve might see and incorporate that with the maximum flow, so that we know worst case scenario, here's the absolute largest CV we need for that valve. So again, minimum and maximum flow are great, but we want to size this with the minimum differential pressure with max flow, and then the max differential pressure with min flow, if we have all the information, because that will give us the entire CV or the entire calculated CV range that valve may see. And we might come back and say, hey, we can't do this in one valve. And a lot of times, and this works out nicely. A lot of times we go back and say, hey, we size it in the extremes, as in the last 2 bullet points here. We say, look, we can give you a valve that handles the max flow, but it's going to struggle at the low end. It's going to be oversized. It might cycle a little bit instead of modulating, or we can give you something that will handle the min flow, but we're not going to be able to do the full capacity. Which is more important to you? So the great thing about this is, by giving us this information and by using this data, we can make good decisions, even if it's beyond the realm of the capability of one valve. We can come back and say, hey, what's more important, max flow? Are you heating things and you want to make sure you have that max flow? Great, then go with this. Or do you need that min flow control? And the beautiful thing about that is, in a lot of these applications where one valve really can't do it, by giving you that choice, we still can keep it into one valve. You just have to give us feedback as to what's more important to you. And then sizing factors. So when you go to a sizing program, ours, anybody's, it gives you the required CV. That's just the exact number that is required in order to pass the flow that you need in those given conditions. But what you want to do, what we recommend, is using a factor for each one. So for example, pressure regulators, we use 0.7. So you take that required CV and divide it by 0.7, and that gives you the optimum CV. So that should be very close to the installed CV. And the reason for that is, when you have the calculated CV, that assumes the valve is at 100% open. So if you're trying to control pressure and the valve is approaching 85, 90% open, it's becoming an orifice at that point in time. And an orifice doesn't control well at all, as I'm sure everyone on here knows. So that's the reason for that sizing factor. And you'll see too, like, control valves are inherently more accurate, and that's just a 0.9, because you can function up to 90% on most control valves and still get good resolution and control. So we recommend, the piloted one's wrong, so I apologize for that. That should be about 0.9. So that's why we have the sizing factors on there, so that the valves are still going to operate in the sweet spot, as the cliche goes, but they're going to give you good performance across the range that you're looking for. And the last note I'd mention on here, back pressure regulators, you see the 0.5, and I get asked about that a lot. You know, why you're essentially doubling the CV on some of those applications. And the reason for that is, a lot of people use these as, you know, bypass, or you're doing kind of pressure relief. And so a lot of times, tied into that same piping is either a rupture disc or a safety relief valve. And depending on how staggered those set points are, you don't want to have a lot of build in a back pressure regulator, because then maybe you're lifting a safety valve, or you're taking the chance of bursting a rupture disc. So we typically put a higher factor on the back pressure regulators, just so that you don't, if you're in a maximum flow condition, you're not jeopardizing a safety relief valve or a rupture disc. Hopefully that makes sense. And I'm going to switch gears. On another topic, tank blanketing. So this isn't so much a challenge, but this is a completely different type of regulator and style. So just wanted to throw that in there. We had not covered this in Regulators 101, but tank blanketing is just the process of providing a blanket or pad of gas above usually liquid level on a closed tank, where there's issues or challenges with the gas could be explosive or harmful to the environment, that type of thing. So you take an inert gas, typically nitrogen, and blanket or pad that device. And then there's usually some type of D-pad or vent that's included. And again, depending on what's inside the tank, it can be vented to atmosphere, or it could actually vent to some type of containment or even flare at times. Why do we blanket tanks? Protection, obviously, people, environment, product, equipment, whatever's in the tanks could be combustible, so removes the oxygen required for combustion. It can prevent oxidation within the tank and evaporation. You don't want these vapors. Typically, there's applications where vapors would be very harmful, so you don't want them going into the atmosphere, and you don't want, and you're also hoping to reduce corrosion within the tanks. Most prevalent gas is nitrogen. There are others, but nitrogen is the most prevalent. And ironically, I have seen natural gas used as a blanketing gas at times also, which surprised me, but that happens. The pressure in the vapor space is sensed and controlled by a pressure regulating valve. The big difference here, though, is the control pressures are typically in inches of water column. So maybe up to 5 inches water column inlet, and then you'll have a vent on there, which can be mechanical. There's a good picture that can be mechanical, and that's maybe at 8. So you've got a normally open valve, and as the product is pumped out, then this valve will allow more nitrogen in to maintain that inches of water column blanket for safety reasons. And then if the level is static, then everything should be closed and maintained. And then if you're pumping more product in, then this normally closed back pressure regulator or D-pad regulator will open and allow that out, allow some of that to vent out so that you don't overpressurize the tank itself. One other key thing, if you're looking at applications like this, and this is the biggest question I get, and it's a challenge for you all as consumers and maintenance folks and engineers. Sensing line should always be attached to the tank. This one's the inlet valve, obviously, so we're essentially doing downstream pressure. And people want to cheat and put it in this line, but you always want the sensing line where you're actually trying to control the pressure. So we're not controlling the pressure in this actual feed line. We're controlling it in the vessel itself. So the same is here on the normally closed back pressure regulator, sensing line on the tank. And yes, I know sometimes you have to have another port added, but this is the appropriate way to do it. You always want to sense in the actual where you're actually controlling pressure, because you could have some turbulence in this or turbulence in this if you were sensing in there, and we don't want that. Why do we blanket, or what do we blanket? So again, anything that could be harmful to the environment, but it also includes foods. I know we do a lot of orange juice blanketing nitrogen, and that's just to keep the oxygen from getting to it and ruining it, basically, is all it boils down to. So there's a lot of different applications, and a lot of it is just preventing product breakdown, particularly in the food and beverage markets. So all kinds of applications. It's not just necessarily nasty chemicals or things like that. There's a lot of different applications and need for the nitrogen blanketing. And that's it. We wanted to keep it pretty brief, a little over half an hour. So hopefully that worked for everybody that's in attendance. Really appreciate your time. The Lesman folks that hosted this have been our representative for about a decade now and are very technically astute, can help you out if you do have applications that result from this, or if you have questions later, if you think of something, email us, or technical assistance at Lesman, whatever you need. But very much appreciate your time. We know everyone is busy, so thanks for tuning in with us.
All right, well, that looks good. Tim, thanks. Really, really good job. I think you covered some great topics, and it was all appropriate for that next level of learning for the 200 class. If you have any specific questions, feel free to give us a call at 800-9-LESMAN. If you don't know your account manager, just ask for me, Chris Modrich, or you can hit me on an email, chrism@lesman.com. And just in general, if you want to know more about the technologies we supply, we have many posted webinars on our website at lesman.com and also at our YouTube channel at Lesman Instrument Company YouTube channel. If there's any other topics you'd be interested in having us cover, we always like to do webinars and help people learn. Again, you can just drop me a note at chrism@lesman.com. So if there are no further questions, this will conclude this particular seminar. So thanks, everybody. Have a wonderful day. We appreciate your attendance.